Yeah. Area of a rug, which is shaped like a rectangle, is 14x squared plus 7x square feet. Factor this polynomial to find the expression for the dimensions of the area of a rug. All right, so area of a rectangle is length times width. So if we come up with the factors of this expression, one of those factors will be the length and the other will be the width. All right, so what we just need to do is set up our equation. And then factor the right-hand side, factor that expression. All right, so in order to do that, I need to identify the GCF. All right, so I need the largest number that divides evenly into the 14 and 7. 7. And then I need the variable that's raised to the lower exponent. Just an x. All right, and that's going to be the multiplier of the binomial that gives us the area. All right, so in order to figure that out, we're just going to take each of these two terms, this guy here and this one over here, and divide them by 7x. All right, so 14x squared divided by 7x. 2x. Positive 7x divided by 7x. Positive 1. All right, and so we're looking for the dimensions of the rug. So we got our factors. So our dimensions would be 7x and 2x plus 1. All right, so length and width. It doesn't matter which is which. Right, so it's kind of a misnomer to think that the length has to be longer than the width. It's really not the case. Right? One dimension is known as the length and the other is known as the width. Now factoring by grouping is just kind of like an added step to what we've already been doing. We basically have to do factoring by Gcf twice. Right? So if you look across your four-termed expression, right? So you got to have four more terms in order for factoring by grouping to make sense. You look across your four terms, you'll notice that there isn't a single, not in every case anyway, there isn't a single GCF that could be applied. So what we do is we split it up. I call it partitioning it. All right. So we split the four-termed expression up. Oh, there's a little spacing issue here. I'll take that as a typo. We split it up based off of commonality, right? Meaning, I would look at my four-termed expression here and say, well, you know what? If it were only the first two terms, I could pull out a GCF. If it were only the last two terms, I could pull out a GCF. But because there's four terms, that's when things start going haywire. So I would, with that in mind, I would say, well, why don't I just split it right down the middle and treat this as if it's its own expression, right? So that expression, xy minus 7x, would have a GCF of what? Just an x. And when I divide each of the terms by x, what do I get? Y minus 7. All right? Now, I could do the same thing on the other end. What would I pull out there? A positive 7. Got to pull out the sign along with it. When I pull out the positive 7, what's left? Y and a negative 7, or y minus 7. All right? So you might think that you're done at this point, but now looking across my polynomial, or my factored form, I have my two terms here. I notice that there's something in common between the two terms. What's that thing in common? The y minus 7, the thing in parentheses. Now I could factor that out also. All right? So I'm going to factor out y minus 7. Because that is what is in common between the two terms. So y minus 7 goes in the front. And what I want to be thinking about, and this is the weird part, is what I would be left with if I were to remove the y minus 7 from here and remove the y minus 7 from there, so just make them disappear, just pull them out, what would be left over? X plus 7. All right, so you look at this and say, well, okay, that was something. How do I know that that's right? Well, I mean, you can take it on faith. If you follow the algorithm correctly, algorithm's a fancy word for basically a set of instructions, but those instructions are split it down the middle, find the common factor for each part, pull it out, then find another common factor, pull it out. You could take it on faith that you did all that right, or you could distribute this out using the double distributing technique and see if you get what you started with. Right? That, I think that might be a little overkill, because again, if you follow the algorithm, if you're confident in your approach, then you shouldn't need to do that. So let's take a look at the second one. Again, partition it right down the middle. Now, it is possible that you may have to rearrange your polynomial first. All right, so if the things aren't naturally grouped together, you may have to move some things around. That's one possibility. Another possibility is what it says in bold here. You may have to see if there's a GCF in play first. All right, so look across the board, see if there's a common factor that could be pulled out immediately, because oftentimes that'll simplify things greatly. All right, so split it right down the middle, right down the pipe. What do we have in common in the first two terms of the expression? 4 and an R. All right, remove a 4 and R from each one by division. What am I left with?
M plus 2.
M plus 2. All right, we're going to do the same thing on the other end, except we're going to remove something else. What's that something else? 3, a positive 3. You got to pull a sign along with it. This is the number one thing that people mess up with this concept. They don't pull a sign with it, and they end up with products all over the place. All right, so you got to remind yourself to do that. If it involves a highlighter, that might not be a bad thing. All right, so this needs to be there in both cases. All right, I pull out a 3 by division. What am I left with? M plus 2. All right, and it's a good thing that happened, because when you get to this step, if you don't have a common factor, a common thing in your binomial, you should start questioning whether you did the previous step correctly. All right, because most of the time, these two expressions will be the same. All right, if you don't get the same thing here, and you did the factoring part correctly, it must mean that you needed to rearrange the expression to begin with. All right, so now I can factor out the commonality. That commonality is the M plus 2 from each term. If I remove an M plus 2 from each part, so I'm taking it out from here and I'm taking it out from here, what am I left with? 4R plus 3. All right, and again, like I said before, either trust in the algorithm or distribute it out and check. Right? For a homework problem, yeah, you're probably not going to check. But on a test, if you have some time left over, of course, use that time to check it. All right. So there's a little example here. It got kind of stuck in the mix. It can be helpful to recognize when binomials are added at inverses of one another. 6 minus a is the same as negative a plus 6, which is the same as factoring out a negative 1. All right. Actually, executive decision, I'm going to do number 3 with you also, because you could split it down the middle. That part people don't mess up. It's pretty easy to see, I think, on the left-hand side of that split, that there's a common n. It's just kind of staring at you. But then on the other side, you have a negative r minus 5. Now again, my goal here, and so this rule is nice, it's a helpful rule and everything, but if you always have in mind that your goal is to have your binomials be exactly the same as one another, then what I should be looking for is another r plus 5. So what would have to be the coefficient of that r plus 5 in order for it to end up being a negative r minus 5?
-1.
Negative 1, you got it. So I'm going to pop in a negative 1 here, all right? So you could factor out a negative 1, or you could do what I just did. Now, that's not the thing that people typically screw up. It's the next step. It's some variation of this step and the next step. You know, it's like a hybrid of the two. What happens often is that people say, well, I don't need the 1 because there's an understood 1 there. So they don't write it. And when they don't write it, they don't get the next step, which is the final answer, r plus 5 times n minus 1. Bless you. What they get instead is r plus 5 times negative n. All right? Because what they'll do is they'll say, okay, well, I didn't write the negative 1 here, so I just have a minus sign. They pull out the r minus 5. They're left with an n and a negative sign. They figure, okay, well, I'll just put them together and make a negative n. All right? It's weird to think that that's something that people will do. It's also weird to think that like 75% of the class at some point will make that mistake. All right? I'm hoping that because I'm bringing it up now that we can avoid that, but that is very, very typical. All right? So you got to be careful about that. And it really only happens in this case, because in this case, you're gonna factor out a negative 4. You're not going to run into that problem because you're not going to just not write a 4. It's people not writing the 1. That's where things go haywire. All right, yeah, so I think I talked enough. Gotta see what time we end here. .38. All right, so you got 12 minutes or so. All right, so your classwork / homework is pages 4 to 6. I'm going to take a look at the weather, see what we're at. Yeah, sure. I've been hearing 3 to 5 inches, so.
On Tuesday?
So once you get to this step, you realize that there's an m plus 2 in part. So that's a common m plus 2. So that's a Gcf. So we're going to factor out the Gcf. Just like up here, there was a common x, so we factored it out. We're just going to use the common factor.
My teacher is not your memory.
Oh, hold on, I just got to turn off the recording. Like right here. This one, you pull out a 3p, that'll give you an n plus 5, and then you'll pull out a negative 4, which also gives you an n plus 5, then you have a common n plus 5.
Guys, 1 and 2 on the next page is actually so easy.
So when you remove the n plus 5 from each piece, you're left with a 3p and the negative 4.
I just sort of wrote it like how you wrote it.